Unit 1 Test Study Guide. Label the following algebraic expressions as rational or irrational. So we're looking at our term 3 is a rational number, but root 47 is irrational. Anything I multiply to an irrational number is always going to be irrational. Number 2, we have 1 over 5, and we've already discussed that a rational number is any term that can be written as a ratio of two integers. 1 and 5 are both integers, so that would be a ratio of two integers, so it would be rational. 0.33, repeating. 0.33, repeating. Remember, anytime we have the repeating bar, we take that value and we put an equivalent number of 9s under it. So now we have a ratio of two terms that are both integers, and so this would be rational. 4.236715. We have what appears to be a non-terminating, non-repeating value. Goes on and on and on forever as indicated by the ... so we are going to identify this as irrational. All right, the product of two rational numbers is irrational. Well, we can think of any two rational numbers, and no matter what they are, when we multiply them together, they are always going to be rational. So if you need to, give yourself some examples, something like 0 times 5. Well, 0 times 5 is 0, that's rational. Or you can have 3 times negative 6, that equals negative 18. Well, that is also rational. And so the statement would be that it is never the case that you can multiply two rational numbers and end up with an irrational solution. The sum of two irrational numbers is rational. Well, let's again give ourselves some examples. If I add 5 plus pi, because pi is an irrational number, then we are going to end up with 5 plus pi, which is still irrational. Pi is an irrational number, and we're just adding 5 to it, so the value of the solution will still go on and on and on forever without ever repeating. Now, if I take a value like pi and I subtract or add the opposite, negative pi, we get 0. Well, 0 is all of a sudden an integer, and thus rational. So this would be sometimes true. Number 7, simplify completely. So we want to find our prime factors, or we talked about in class being able to find perfect square factors. And so in this case, we're going to end up being able to do a little bit of both, because our first prime factor is 2. We divide by 2, and we end up with 36. So this is the square root of 36 times 2, and we should recognize that 36 is a perfect square, and thus we can pull one of its pairs out. The square root of 36 is 6. Now, if it makes more sense to you, these two values are getting multiplied together. We can certainly break this apart to represent them getting multiplied together. The square root of 36 times the square root of 2. And then we just simplify each individual radical. So the square root of 36 is 6. Square root of 2 does not simplify, and so we end up with 6 root 2. Notice that we got the same answer no matter which root we took. Next problem. 2 times root 18k to the 5th m to the 3rd. So we want to factor down our 18. again, I'm going to see a 2 and a 9. A 9 is a perfect square, so that's a nice number to see. One of the things that I get into the habit of doing whenever I'm taking the square root is trying to make my powers even numbers when possible. You don't have to. I think it complicates things a little less. So k to the 4th times k to the 1st is the same thing as k to the 5th. Times m squared, m to the 1st is the same thing as m to the 3rd power. So again, at this point, if we want, we could put everything in the radical. We would have 9 times 2 times k to the 4th times k to the 1st times m squared times m to the 1st power. Now, I'm not forgetting about this 2 here. We need to remember to bring it down. So now I'm going to look for my perfect squares. Remember, we made these even powers so that they could come out of the radical as well. If it is not boxed, it's staying in the radical. So let's clean up the radical. The radical is left with root 2 k m. And we need to pull our items outside of the radical. So we had a 2 outside. I'm going to bring that down. We're going to multiply by the square root of 3, or square root of 9, which is 3. We're going to multiply that by the square root of k to the 4th, so we're pulling out half of the k's because that would be the correct number of pairs. So k squared. We're going to multiply that by the number of m's. The square root of m squared is just m. And we can clean up our finalized answer. Two times 3 is 6. K squared m times the root of 2 k m. Alright, let's look at number 9. See if I zoom in a little bit. That'll take care of some of that sun glare. Alright, so we have the cubed root of 8a to the 6th b squared. Remember that the cubed root means we're looking for sets of 3's. So we'll start with our 8. Can be divided by 2 and 4. 4 is divisible by 2 and 2. Now, I didn't leave it as a square root because we're not interested in pairs anymore. Rather, we're interested in seeing how many sets of 3 there are. Now, the other thing I like to do is go ahead and break up any powers down. So I want to see sets of 3 of those as well. So a to the 3rd power times a to the 3rd power is the same thing as a to the 6th power. And while we're writing things down, I'm going to go ahead and write down the b squared so that I don't forget that it's up there. So let's clean up what we have. We have the cubed root, and we're pulling out sets of 3. So notice I have one factor set of 3. That's a 2, so that's coming outside. I have a set of a's and another set of a's, so times a times a. And I have a b squared that's going to remain inside the radical. So let's finalize this answer by multiplying things together. 2 times a is 2a squared times the cubed root of b squared.